All right, so we are going to, um, okay. So this is lecture 2, Mechanical Vibrations, 2nd of April, 2021. Okay. So last time we discussed about mechanical vibrations and of course only introduced some general mathematical um, background and historical perspectives. And we want to start now the course. But before I do that, please make sure to come on time because it is unfair to others. First of all, this clinking noise that generates everybody, anytime anybody comes in late, and I'm addressing those who came in late. Please make sure do not come late because it causes interruption and also is a nuisance for those who have been on time. But anyway, we want to discuss mechanical vibrations. And like any course, when I start, I would like first to give you sort of an overview or a broad perspective on what is the objective or the objectives of the course. Okay. Of course, any course you study, there is certain objective behind that, right? In mechanical vibrations, the objectives are twofold. One, anytime a system, what is mechanical vibration? Mechanical vibrations means you have a structure in a mechanical system that is acted upon by an external vibratory force or time-dependent force. So the first objective is we want to understand, okay, the oscillatory nature, the oscillatory nature of the system. That is, when a structure is subjected to an external force, okay, what happens? How the system is going to behave under the action of that load. The second objective is, okay, if vibration is something that causes a system to vibrate, right? Then we may have actually either interest or our goal is to control that vibration, not letting it damage the system, for instance, or mechanical vibration, in fact, may be something good that we may utilize to do something good to a system. The example of controlling the adverse effect of mechanical vibration is, for instance, an earthquake. You have a system or a structure that is subjected to a vibratory load, and we want to prevent damage to that system. An impact load or a blast load that may destroy a structure. How do we design a system that would resist a devastating or catastrophic, potentially catastrophic effect of the vibration? But there are also cases that the vibratory motion is something good. We can use that to do something that is in fact productive. The engine of a car is a vibratory source of motion, is a cyclic motion or whatever. It causes the motion of a car. The jet engine in an airplane is a source of a vibration. It is a good thing that causes or helps us to move a huge structure, put it in the air. So vibratory motion can be good or bad. Case one, we call that undesirable vibration. And we want to isolate that, okay? The second case, we call that a desirable vibration, okay? See, we're talking about, or last time I started actually talking about, mechanical vibration, and it said that, we are going to study the mechanical vibration of a system. And I told you that mechanical vibration can be described by this schematic diagram. Okay, that is, in other words, a mechanical vibration can be simply described by a diagram like this: that you have an input that is a force, or can be actually a displacement that causes the vibration. Earthquake is a good example, or an acceleration, and the response. So studying mechanical vibration is nothing but understanding the meaning of this schematic diagram and each element of this diagram. If you look at this diagram, or this system diagram, it consists of three elements or three pieces. What are these three elements? Input, okay, system, and response. So in order to fully understand this, or to fully understand mechanical vibration, and what we are going to do in the course is to understand these three elements. What is the input? Input can be a force or a displacement, but also, depending on the type of input, we may have different types of vibration. This input can be a deterministic source, a deterministic force. Okay, the engine of an airplane generates a cyclic motion that can be measurable with the mathematics tools that we have. But the source of the input or the vibration can be random, cannot be measured or determined by the type of mathematics that we are used to. We call this deterministic vibration or random vibration. So depending on the type of input, vibratory motion or the vibration of a mechanical system can be categorized in two broad categories: deterministic vibration and random vibration, where random vibration in itself is a completely different class of vibration, which requires a different even mathematics, which we call that the stochastic calculus. The second element in this diagram is the system. What we mean by the system is this: a system, which is really the key focus of our study, is really a bridge between the real world, okay, and the world of mathematics. In other words, what we are talking about is that we are going to develop mathematical tools that can represent this system in order that we can fully study that system. We'll talk about that in a minute. And the third component is, of course, the response. Response means the structure has been subjected to a vibratory motion. We want to know how it is displaced, or in different component of the structure, what kind of dynamic stresses may develop. So these are the three essential components that fully describe what we're going to discuss in this course. Okay? I emphasize that the system is the first component that we want to study. What is the meaning of a system? In real world, we deal with the structures, a building, a light pole, a bird, a tree. These are all systems or structures, regardless of the shape or the nature. However, in engineering mechanics, you cannot say, I am going to study this structure. If you tell me that I'm going to study this structure, the first question I ask you is how? That means physically, how do you want to deal with that structure? In order to deal with that structure, we need to develop a tool, a mathematical tool that mathematical tool can represent the kind of information that we want to identify or extract from the behavior of that structure. Let me be, uh, sort of tell you or a simple example that you have dealt with in strength of material. In the strength of material, you wanted to know one thing, and that one thing was that if you have a structure subjected to a load, how that structure deforms, deformation. So in order to measure the deformation of a structure, you said the structure can be described depending on how it is loaded and how it is deformed by simple mathematical tools that we call them some names. We came up, for instance, with a name for this, which we called that a beam. A beam was a tool or a model that could represent the bending of the structure under the action of a bending moment or under the action of a shear force. Okay? But this mathematical tool or beam could be represented by a simple mathematical function, which was this. If you apply a moment, bending that to this beam that causes a displacement, this bending moment is related to the deformation that takes place in the structure and some geometric and material characteristics. But the point was that by understanding what it is that we want to identify and measure in the system, its bending, its displacement, our bending stresses, we define a model called a beam or a bar. The difference was between the two was that a bar is subjected to only a force that acts along the direction or the axial sort of direction of the structure. In here, in beam, you have a force that can actually act perpendicular to the, for instance, the uh, axis of bending of the structure. But nevertheless, these were models, or even a shaft. These models could describe what we were interested in stress analysis. And that was how we can relate a force to deformation. And that was the only thing that we were dealing with in the strength of material. Okay? And of course, in that course, the force that we were dealing with was time independent, okay? Constant, okay? And also we made certain assumptions. The assumption was that as far as the geometry of this system goes, or the structure goes, and its mathematical and its material characteristics, the deformation that takes place can be linear or nonlinear. That means this force can be related to this deformation either through a linear manner, that is through a constant coefficient, which we call that a stiffness, or can be related to sort of more complex way. So that was the strength of material. In dynamics, you studied the system or the behavior of the system under the action of an input, but not only considering that, but also you all were interested in seeing what happens to the inertia, which is another characteristic or inherent property of a system. Okay? So far in all the courses in engineering mechanics that you have studied, you have only been faced or experienced two things that are only two of the characteristics of a real world structure. These two characteristics that you have studied have been either the stiffness, which is a measure of the ability of the structure to resist deformation, or the mass, which is the ability of the structure to resist motion, which we call that inertia. A system that for the first time you're going to study in mechanical vibration is a system that represents all the inherent characteristics of a real world structure. So we need to know what are the three major characteristics of any real world structure so that we can truly represent that system and study the behavior of that system under the action of a load. Any system, regardless of its shape and function, that you encounter in nature has no more than three inherent characteristics. If you can understand and being able to physically and mathematically describe those three characteristics, you can describe that system fully, and you can develop a mathematical tool that represents all behaviors in a real structure that you're interested in identifying. Remember, I told you Mr. Galileo was the first person who actually could develop this approach analytically and mathematically to describe a system. So what are these three characteristics? Any system in the world has the ability to resist deformation. This is the first characteristics that every system has. And what you have done, you have studied that. We call this ability or characteristic the stiffness. And I will discuss that in more details in a minute. Any system in the world has the ability to resist motion, and we call that inertia. Inertia is that component or the characteristic or the attribute of a system that resists motion. Then any system also has the ability, as it is going through some deformation or subjected to motion, absorb or dissipate energy. Any structure in the world has no more than these three abilities. You cannot think of any physical structure, including your own body, that has more than these three abilities or characteristics or attributes. Okay. So if we can find ways to describe these three attributes, we have been able to completely and fully describe a system. Okay. But before we do that, okay, I should also um, say this, that in order to deal with a system and develop this model and study it, we need to have follow certain laws of mechanics. And the law of mechanics that we will be dealing with would be the second law of mechanics, which is you have also dealt with it in dynamics. What is the second law of mechanics? Second law of mechanics tells us that, and some of the all the applied loads, time-dependent loads on a system are related to the product of the inertia and the acceleration in a system. This is the mathematical concept, or in the uh, law of engineering mechanics, that would be governing law that would be used to study the behavior of our system. So, so let's go back and talk about those three attributes. I said stiffness, and the stiffness is a measure of the ability of the structure to resist motion. The kind of, first of all, behavior when it comes to the deformation of the structure that we will be dealing with, including in this course, is that the system deforms linearly. That is, we do not exceed the yield limit. Or, in other words, there's a linear relationship between the applied load and the deformation that our system uh, sort of does. If we make that assumption, we can say that in order to understand the ability of the structure under the action of a force and how it deforms, we need to identify what we call the stiffness of the structure. What is the stiffness? The simplest case, the simplest way to describe a stiffness is this: a spring. A spring subjected to a force deforms, goes through deformation, and for a linear behavior, this force and displacement are related to each other through a quantity which we call a stiffness. As long as any system behaves linearly and the force is causing a displacement, that displacement is related to the force in a linear fashion, regardless of the shape of the system and how complex it might be, we can identify what this stiffness element is. In fact, if you think of just a spring system, what is this stiffness quantity? This stiffness is a force that causes a unit displacement. In other words, if you apply a force in a system that causes a unit displacement, that force is that the stiffness of the system, and you can measure that. Okay? We get to that in more details. But as far as the ability of the force to resist motion, or studying the ability of the structure to resist deformation, we need to understand what is a stiffness. The second element is the mass. Mass is the easiest component of a system to identify because you can directly measure that. It is that component that resists the, basically the gravitational, resisting the gravitational acceleration. Okay. And the energy absorption is, in fact, the most complex element of this system that we're talking about, because that is something that you haven't even studied in previous courses. It's a very complex component. We'll get to that. So let me say that by now we know that how to understand what mechanical vibration is all about. Okay, mechanical vibration is talking about motion and how a system is behaving under a motion. And this motion can be either translational or rotational. And understanding mechanical vibration requires understanding the system that consists of these three elements that I talked about. But there are also other terminologies or system characteristics as far as their behavior goes that we need to understand and define before we move forward with developing the tools to identify these three components. The most important of these terminologies is what we call degrees of freedom. If I give you a structure under the action of a vibratory load, you would see that every part of the structure is going to move. So the first question you ask me is that, wait a minute, you're telling me that you're going to give us the tools that enables us to understand the system and measure and response of the system, but this system is behaving so complex. So I tell you this. I'll tell you that, yes, you're right. Even if you look at a simple beam, when it is moving, this beam is made of infinite number of these masses that comprise this beam. So if this beam moves in certain direction, every little one of these masses is going to move in this direction, or may even rotate in more than one direction. Every piece of this little piece of this structure, its motion, the direction it's moving, is called a degree of freedom. So a degree of freedom means the way that the small piece of this structure moves is a quantity that describes how each piece of the structure moves. However, so in other words, if you have a structure, even a simple beam, it has infinite number of degrees of freedom because you have infinite number of these masses that move, each of them in a different direction. However, we can make our life easier. Think of a beam that, for instance, this tip of this beam is moving in this direction. If I can find a relationship between the direction of the motion of these individual masses and the motion of this single point at the tip of this beam, okay? Or in other words, I can represent the motion of every single part of a structure with the motion of a single degree of freedom, we can say that this structure can be represented by a single degree of freedom. And in fact, the first thing we do in studying mechanical vibration is how in the world I can identify in any system a single point, a single degree of freedom that its motion can be related to the other members, other degrees of freedoms. In other words, other degrees of freedom will be dependent on this degree of freedom. So the structure can be represented by only one degree of freedom or single degree of freedom. This is a terminology that we'll get to that, okay? Or let's not just that, let's make the assumption that every system that, for the time being, since we are not talking about how to set up these degrees of freedom and relate them to a single degree of freedom, but let's assume, and that's the first and the most important assumption to begin with that we are going to make in this course, that every system in the world that you can imagine, its motion can be described by only one degree of freedom. I'm not showing you yet how to do that, but I'm asking you to accept that, because the entire course will be based on the assumption that the motion of a system, regardless of its complexity of the system, can be described by only one degree of freedom. So, with all that said, let me summarize, okay? What we are going to do in mechanical vibration is twofold. The study of mechanical vibration comes down to two tasks. One is how to model any system, okay, as a single degree of freedom system, and two, how to find or measure the response of this system. Response means what? A displacement, a deformation, stresses, and whatnot. And of course, as far as measuring the response of the system, we are going to study the response of the system in two broad situations. One, the system has been subjected to a load, now the load has removed, so we call that free vibration, or the case that the system continues to be acted upon by force, we call that forced vibration. So with that said, okay, with that introduction, let me summarize what we have done and move forward, okay? And what we are going to do is this. We said that mechanical vibration is the study of a system that consists of three components: mass, deformation capability, energy dissipation capability under the action of a load. And this system only moves in one direction or has 1 degree of freedom. Okay? So this is what we are going to do. We are going to show you, okay, that the entire course of mechanical vibration then is going to be the study of what we call a single degree of freedom system. That is a system that is defined by three components: the mass, a stiffness, and energy dissipation capability, subjected to a force that is time dependent, and we want to measure the displacement or subsequent quantities that result from displacement of this system. But this is going to be what we will study in mechanical vibration. Okay? A single degree of freedom system. Okay? So, and in order to do that, we need to, as I said, to know how to model a system as this, and then the next task, how to find the response. Okay? So to set up a meaning tool for dealing with this, in other words, to set up a mathematical tool that enables us to study this system that we said it is going to be all that we will be doing in vibration, and schematically described by this motion. We need to use, as I said before, second law of mechanics. And the way we do that, we have seen that, is by looking at our system and set up its free body diagram. This is our vibratory system. Let me re-emphasize. We do not know first what this means, and this means. But if we know, given that any structure can be only described by fully described by these three components, I claim this is every structure in the world. Now, how am I going to study this every structure in the world? By developing the right mathematical tool. This mathematical tool can be developed by setting up the free body diagram of this vibratory system. What do I mean by that? You have a mass, it is vibrating. So in other words, due to the action of an external load, this mass is experiencing an inertial load, a load of inertia. Its motion is resisted by these two sources of resistance, which we call force of deformation or stiffness and dissipation of energy force. And this is the free body diagram. Once we set up this free body diagram, by writing the second law of mechanics, we can find the mathematical tool that we need. But before doing that, let me tell you this. In dynamics, this is the free body diagram you set up to solve the problem. In mechanical vibration, I prefer a different approach because I like to establish an analogy between mechanical vibration and statics. In statics, we had summation of forces acting on a system is always zero. So now, wait a minute. If this is my vibratory system, and I put a force like this, which is resisting this force. In other words, it is acting in the opposite direction of the force. This system is going to be in equilibrium. That is, I can use this equation to describe this system. And how do I describe that? By applying this equation of equilibrium. You do have this force, this force, this force that are going to be equal to the applied load. This relationship describes the equilibrium of this system. But let me tell you this. We said that this stiffness force is a force that is linearly related to the displacement or deformation of the system. The energy dissipation force, which we call that a damping force, is not as simple. In fact, the energy dissipation characteristic in a real structure is a lot more complicated than the displacement of the structure under the action of load that you have already seen. This can be fully described or derived. Energy dissipation is something that you cannot derive it. It depends on so many factors, including materials, velocity, or many other characteristics. For that reason, in mechanical vibration, we assume or make an assumption about this force, or set up this force in an arbitrary form that is easy to deal with. We say that this force is linearly related to the velocity of the system, and we call that a linear damping force. So therefore, this equation that I wrote down comes down to this. Okay? This is what I call governing equation of motion. The objective of mechanical vibration, and let me write that down, this force is called the lumbar force. Okay? The lumbar force is something you put in the opposite direction of motion to make the dynamic problem a static problem. So the objective of mechanical vibration is nothing but solving this equation of motion. Why is it that now all of a sudden the entire objective of mechanical vibration ended up in one mathematical equation? Because this mathematical equation has all the information that I said this system schematic diagram of a structure, which is system diagram, represented. What? This, any real structure subjected to a load, right, is, has in it a system that we are going to study. The system, we said, that comes down to only three attributes or characteristics, and this differential equation contains all of those, right? A study of the system vibration requires understanding of the input, which is a forcing function. This differential equation has this forcing function on its right-hand side. Studying mechanical vibration, I said, is understanding how to find the response of a system. System response means displacement, deformation, and so on. This differential equation has this response in it. So this differential equation, which we call that equation of motion, represents everything in mechanical vibration that we are interested. It represents this single degree of freedom system, right? It represents what we are measuring, and it represents what is the input of this system. Okay? So studying this system is all we are going to do in this course. But don't forget, I would emphasize again, in order to study this system, we need to do two things. Address these two objectives. The first and foremost, it is important to know how to set up this single degree of freedom model, okay? That is, we need to find what is the meaning of M, K, and C, or better call them equivalent mass, equivalent stiffness, and equivalent damping in a system. In other words, if you have a big structure, what is the inertia in that structure? How does that structure deform statically under the action of a static load? Or what is the stiffness of that structure? And what is the damping force or damping coefficient or component, energy dissipation component in that structure? So once we spend 2 or 3 weeks in doing that, we have been able to model any structure in the world by this single degree of freedom system. And once we've done that, then the second objective is the solution of this equation of motion. And this equation of motion that I'm going to rewrite again here, okay, as you can see, okay, we are going to study that in two completely distinct sort of categories. Category number one, is that first we assume that the forcing acting on the system has disappeared. It was there, moved the system is vibrating, now there is no force. We call that free vibration or free vibratory motion of the system. Second, we are going to look at the behavior of the system while that force is acting on this system. So we will be studying forced vibration of this system. But in each of these, in order to make our life easier, we do further subcategorization. We study both of these cases when we assume the system is either undamped, that is, no energy dissipation exists in the system, or, is damped or is undamped in both cases. So either the system is undamped or damped. So basically, there are 4 cases that then we will be studying. Free vibration of undamped systems, free vibration of damped systems, forced vibration of undamped systems, and forced vibration of damped systems. That's what we will be studying in this course. However, as far as the forcing function, or when we talk about force vibration, we will look at a variety of different forces, time-dependent forces that may be acting on our structure. So with that said, I'm going to stop here. And if you have any questions, I'll be happy to answer those. Otherwise, we'll pick it up from here next time. Questions?
Professor,
Yes.
going back to the like when you got the equation of motion and you had like the D'Alembert force or whatever, is that just
Mhm.
reversing the like the force from acceleration? Like what why can
Exactly.
you just revert? Okay.
Exactly. If, in other words, you have a vibratory motion and you say, okay, I put the inertial force in the opposite direction, what happens? System is going to be in equilibrium now, static equilibrium. So that's called the Lombard principle. The Lombard, what he did was exactly that. And so you can simply write sum of all forces, including the inertial force, is equal to zero, except that the inertial force acting in the opposite direction. We'll see that you will see that how we are going to apply this. By having said that, I can tell you that next time, where what we are going to do, we will start by, the first case, free vibration of undamped systems. So that's the first thing we do. We looked at the model that we have, which is now going to be a simpler model, okay, that it is not acted upon by any force. So the equation of motion, if this is moving in this direction, will become simply mu double dot plus ku is equal to zero. So that's what we're going to start next time. But we're not going to yet study that with having the purpose of finding the response. But as I said, we will spend the first 2, 3 weeks to understand how we can actually model a structure by this simple model. All right.
Thank you so
Have
much.
a, you're welcome. Have a great day and see you during my office hours.